Hello.
Hello.
Hi. Hi,
Hi.
Jingyin.
Hello, nice meeting you.
Hi, good to meet you.
Good to meet you. So probably I'll try to share my screen to see whether.
Oh yeah, sure. You can share your screen.
Okay, give me one moment. Can you see the screen? Or?
Yeah, I can see it, but I can't hear you very well. Your voice is very low.
How about now?
Okay, now it's a bit better.
Maybe I'll try to put my
Actually, it's a little, I don't know, fuzzy or something. Yeah.
Yeah, maybe I'll try to put my earphone. Give me one moment.
Hola, David.
Hello. How are things?
Good. So far, so good. Very hot here.
Yes, I'm still in Indiana right now, so it's not so hot, but
Okay. Probably we should wait a few minutes.
So can you hear me better now? Or?
It's a little better.
Okay, so maybe I'll try to speak louder.
Okay, yeah, that's better. Is it just me or is it other?
it sounds okay to me, but I don't know.
Oh, okay. Yeah. Okay, maybe I'm wondering.
Happy Friday.
Yeah, happy Friday.
Friday, everybody. Good to see many people.
Yeah, thanks for so much for agreeing to talk. Looking forward to it.
Thank you.
Okay, maybe it's a good time to get started. So we're happy to have Jingyin Huang talk about measure equivalence superrigidity for some generalized Higman groups.
Thank you very much for the introduction, and and also I thank the organizer for inviting me. So it's my pleasure to speak over here. I should first say that this all what I'm talking about today is going to be joint work with Camille Horbez. Okay, so I want to just start by reminding some of the basic definitions. So I apologize if you are already quite familiar with this. I believe some of you are already quite familiar. So first I want to remind you the definition of measure equivalence. So it first comes as a measure theoretical analog of quasi-isometry. So recall that a map between two metric spaces is a quasi-isometry if it satisfies these two conditions. The first condition just says the map is L by Lipschitz, but after some bounded error A. And the second condition says that the map is almost surjective, but up to some boundary error A. So it's going to be a coarse version of Lifshitz equivalence. And then so Gromov proposed a project to doing a classification of all finite generated group up to quasi-isometry. And then so somehow you see that the definition of quasi-isometry was referring to some metric, and there's a way to turn a finite generated group into a metric space by looking at the word metric. And so in the same paper where Gromov proposed this QI classification, he also make another definition of the quasi-symmetry, which does not quite referring to the word metric of the group. And he's sort of the way he think about it. So he observed that if two groups are quasi-symmetry, if I can find a commuting action of these two groups on the same locally compact space, so the action, so this X is just a topological space, and the action is just by homeomorphisms. And the action is supposed to be proper discontinuous and the co-compact. That means X mod out one of the group, either of the group should be a compact space. So the interesting thing is that this definition does not refer to any metric on the group, but yet they are actually equivalent. And it's actually not too hard to say this. Not too hard to see these two definitions equivalent. So you can just take, in this case, you can just take X to be the set of all ALA quasi-symmetries from this group G to group H, equipped with the topological pointwise convergence. And then that's the X one can use to prove this observation. Okay. So now, then Gromov make this definition. So he call this kind of thing a topological coupling between two groups is just an action of G times H on some locally compact space by homeomorphism, such that each factor is proper discontinuous and co-compact. So now then he proposed a measure theoretical analog of this concept of topological coupling. So this the definition of measure equivalent coupling. So now we'll consider two counterpart groups, G and H. And now, again, so we want a commuting action. So we want G times H. So now here, instead of acting on a topological space, so I'm going to acting on some measured space. And instead of the action is by homeomorphism, I want the action to be measure preserving. And then, so now, in the topological setting, we also want the action to be proper discontinuous. So here I replace the proper discontinuity by require each action to be free. The action of each factor, G or H, is free. And then, so now in the topological setting, we want the action to be co-compact. That means X mod G, X mod H are co-compact. So now here, the measure theoretical analog is that we want each of the action G on and action of H has finite measure fundamental domain. Okay, so as you can see, this would be a sort of very natural analog if you just try to transport this topological definition into the measure theoretical category. And then so he made the following definition that the two groups are measure equivalent if there exists a measure coupling between them. Okay, so this is sort of the beginning of the story, and then I should give you some very quick examples. So every group turns out to be measure equivalent to its finite index subgroup. In this case, what you do, you just have okay. So what we here to see a group is measure equivalent to its finite index subgroup, we can consider the left action of the group on itself and the right action of the finite index subgroup on itself. These two actions commute, and then the group has a counting measure, and this is going to satisfy the definition of measure equivalence coupling. And then another thing to have in mind, which is slightly harder to see, is that if I take a group, if I take the quotient of the group by finite normal subgroup, this is also measure equivalent to the original group. Okay, and then another example to have in mind is if I have two lattices in the same Lie group, they're going to be measure equivalent. So here lattice means that a discrete subgroup with finite co-volume. So now, if I want to construct, for example, here, if I want to construct a measure equivalence coupling, I'm going to take the left action of one lattice and the right action of another lattice on the D group. So this will give commuting actions. And I can also treat this group a measure space by just looking at a Haar measure. And in this case, so it's going to satisfy the definition of measure equivalence coupling. So here, the finite covolume is going to give you the finite measure fundamental domain. So as an example to illustrate this, so we know that the free group with two generate and the fundamental group of the surface with genus bigger than 2 are measure equivalent because they are all lattices in the isometry group of the hyperbolic plane. Okay, so now I think so there's another viewpoint of the measure equivalence. This notion of measure equivalence is from the side of ergodic theory. Okay, so now I also want to just remind some definition very quickly. So now here we're going to consider a probability measure space, and we consider actions, which is probability measure preserving ergodic. Okay, so now recall that two probability measure preserving actions are Ob equivalent if okay, so here X and Y are probability measure space, and so the Ob equivalence means that there is a measure space isomorphism, and this isomorphism preserves the orbit of the action. So it send orbit to orbit. And there's also this also gives you a definition of group. So we say two counterpart groups are orbit equivalent if they have free ergodic and probability measure preserving actions on probability spaces that are orbit equivalent. Okay, so now I want to what I want to explain next is that this notion of orbit equivalence is actually very closely related to measure equivalence. Okay, so for that, I want to there is a slightly more general notion called the stably orbit equivalent. So which is a slight relaxation of orbit equivalent. So again, I'm looking at two probability measure preserving actions on two probability measure space by two groups. And we say they are stably orbit equivalent means that I don't see the orbit equivalent in the whole space, but I can see the orbit equivalence in a subspace. More precisely with the definitions that suppose there's a positive measure subset X prime and a positive measure subset Y prime. And a priori this X prime and Y prime does not to have the same measure. So now let's assume there's a measure scaling isomorphism. So it's basically a measure isomorphism, but just the scale as long as you scale X prime and Y prime to have the same measure, such that if I just look at this isomorphism restrict to this subset X prime and Y prime, then it's going to preserve the orbit when you restrict to the subset. So this is like a relaxation. So you only see that orbit are the same to when you restrict to some positive measure subset. Okay. And then the connection of all this with measure equivalence is made by Fuhrman. So what he shows is that if I have two countable groups, X and G, that measure equivalent, if they admit free ergodic probability measure preserving actions that are stably orbit equivalence. So in some sense, somehow the so what's going to happen in the rest of the talk, we're actually going to work with stably orbit equivalence. So that's sort of more easy to squeeze information out of the measure equivalence. Okay. And then, so now I want to say that this viewpoint to connect measure equivalence with orbit equivalence, which also give rise to much more examples of measure equivalence groups which are measure equivalent to each other. So let me just mention this deep theorem by Ornstein and Weiss. They prove that any two ergodic probability measure preserving actions of any two infinite counter amenable group are actually orbit equivalence. So this is a very sort of a very flexible. This basically tells you there's a lot of flexibility for their action. And then, so as a consequence, we know that if two groups two groups are Ob equivalence, then in particular they are stably Ob equivalence. And then from Fuhrman's result, we know that any countable infinite amenable groups are measure equivalent to each other. So this shows that this notion of measure equivalence is actually quite flexible if we just look at countable amenable group. In particular, you can deduce as a corollary that all the free abelian groups are measure equivalent to each other. That's certainly not true for quasi-symmetry. Okay, so in general, the quasi-symmetry and the measure equivalence, they behave very differently, despite that definition sort of looks similar. Okay, and here will be one example. Okay, so now I want to also say that despite this sort of flexibility in the case of amenable group, so there's also several very amazing rigidity result. The first one would be this theorem by Fuhrman, which happened in the which is proved for higher rank lattices in higher rank simple Lie group. So basically, so I think if you ever haven't heard about high rank simple Lie group, then you can just take G prime to be SLNR, and I take a lattice which is SLNZ. So basically the theorem basically says that if I take any countable group which is measure equivalent to SLNZ, then that countable group has to be more or less a lattice inside SLNR. So this is a very strong rigidity theorem. And I should also say that in the mapping class group side, so there's also a very strong rigidity theorem. So basically what Kida proved is that any countable group measure equivalent to a mapping class group of a surface is virtually that group. So virtually means that these two groups are isomorphic up to passing to finite index subgroup and the modeled out finite normal subgroup. Okay, so this is a very strong rigidity statement if we try to compare to the amenable case. And I think the most recent progress in this direction would be this theorem by Girardel and Horbez. So they prove the same result for out of Fm. So any countable group measure out of Fn is also virtually out of Fm. I should also say that somehow all these theorems are true if I replace measure equivalent by quasi-symmetry. So for some mysterious reason, so they sort of align up for this, at least the mapping class group case and a higher rank simple case, higher rank simple Lie group case. And people conjecture that for out of Fn, there should also be a QI rigidity result, basically of the same statement, but it's still nobody knows how to do that right now. Okay, so this is just a very quick survey about what's known before about this notion. Let me also mention that there are some group property which is invariant and measure equivalence, like amenability is invariant and the property T and Hagra property. Okay, so nowadays there's a lot of invariance you can use to distinguish groups. Okay, so now I want to say a little bit more about how this theorem is proved. So, for example, the scheme of what we're going to do. Well, so my goal today is to prove a sort of a similar rigidity theorem, but for the class of Higman group, and then the strategy I'm taking is a general strategy which is used commonly in the proof of measure equivalence and quasi-symmetry. So I just want to say a bit more about sort of a common strategy. Okay, so this is certainly not the unique strategy, but it's used fairly common. Okay, so let's say let's take a G to be some countable group, and say we will have a choice of a collection of subgroup. Okay, the strategy is more or less so in the first step. So in the QI side and in the ME side, there's always a way to reduce if you want to study groups quasi-symmetric to G, or you want to study group measure equivalent to G. There's a way to reduce to the study of self-quasi-symmetry or self-measure equivalent coupling. Self-measure equivalent coupling just means coupling of G times G with itself. Okay, this, okay, so modulate this reduction. So I think the first step is always shows that let's say our quasi-isometry or our measure equivalence coupling is going to preserve the element in this collection of subgroup in some appropriate sense. Okay, so I'm going to explain later what do I mean by preserve in the ME sense. Okay, I won't explain in the QI sense. And then so also preserve the intersection pattern of the how this subgroup intersect with each other is also preserved by the QI or by the ME. Okay, so that's one step. And the second step is usually more combinatorial. So we want to say that somehow the intersection pattern of the subspace is rigid in the sense that you can have all the information with G from the intersection pattern of the subgroup. So again, so this is something I'm going to make precise later. Okay, so and the second step is usually quite combinatorial. Okay, so this is basically I give you a collection of subgroup. I trying to recover information over the ambient group by just looking at the combinatorics of how the subgroup intersect each other. Okay, so that's sort of what the step 2 doing. And then so somehow this should be the one strategy we're going to take today. And then so just a summary. So the upshot is that we need to find a robust collection of subgroups, such that on one hand, it serves as an invariance under the measure equivalence or quasi-isometry. On the other hand, it has some form of rigidity. So some form of combinatorial rigidity. Okay, so this is the strategy I want to mention very briefly. Okay, so now the next thing is I want to sort of start to motivate what we want to do today. Okay, so I want to explain, let's say I have a group and have collection of subgroup. What does it mean by a self measure equivalence coupling preserve the subgroups? Okay, so this is one step. Step 1, I want to explain the step in more detail. Okay, so again, so from Fuhrman's work, so here it's actually easier to work with a stable Ob equivalence. So in this case, I'm going to consider the question. So let's say I have my group G, and I'm going to have 2 actions. Let's say free probability measure preserving ergodic action on 2 probability measure space that has stable Ob equivalence, and want to somehow formulate what does mean by the stable Ob equivalence preserve the collection of subgroup. Okay, so now to make things not so technical, I'm going to make some simplifying assumptions. So first, let's just consider Ob equivalence instead of stable Ob equivalence. And second, because Ob equivalence means that there's a measure space isomorphism between X and Y, so I'm going to just assume X equal to Y by just identify them. Okay, so now I want to explain what do I mean by Ob equivalence between these 2 actions is going to preserve this collection of subgroup. So now I think the best way to see this is to look at the Ob equivalence relation. This means that if I have a group acting on the space, so I can define an equivalence relation. So 2 points are equivalent if they are in the same orbit. So now we have this G acting on X is going to give us an equivalence relation, which we call an orbit equivalence relation because it comes from the orbit structure of the action. Okay, so now if I take a subgroup, then it's going to give you a sub-equivalence relation by just consider the restriction of, let's say, my first action rho 1 to the subgroup. Okay, so now I want to say whether, okay, so now the question is, so this sub-equivalence relation comes from restriction my first action to some subgroup. Then we want to ask what if we test this sub-equivalence relation against my second action? Does that also come from some subgroup? Okay, so here is sort of my hope that this sub-equivalence relation comes from the restriction of the first action. Also, if you trying to test this sub-equivalence relation, then it also comes from the rho 2 action when restricting to some subgroup from my collection. Okay, so let me mention that here, since these two actions are orbit equivalent, so they will give you the same orbit equivalence relation because these two actions has the same orbit. So now the question is, if I look at a sub equivalence relation, which come from action of a subgroup respect to the first action, then whether that sub equivalence relation also come from an action of a subgroup respect to the second action. So that is sort of the, if this is actually true, then we say that this collection of subgroup is preserved by this orbit equivalence. Okay. Okay, so any
It
question?
seems like a really strong requirement. Maybe I'm misunderstanding. So you're saying that
Yes.
you have
So
two
sorry,
actions of G,
Mhm.
and they're both like essentially free actions with the same orbits.
Right. Sorry. So yeah. So I think I'm sort of, yeah. What I claim here is much stronger than what I can actually prove. So
Oh, okay. Okay.
yeah, so okay. So this is I think what we in the end prove is that this is still true, but we have to partition the probability space into countable and many pieces.
Oh, okay.
So I sort of so in other words, so if you do a partition, then in each of the pieces, you see that the sub-equivalence relation comes from action of some subgroup respect to the second action. But on different pieces, the subgroup may not be the same.
Oh, okay. Still sounds like a strong.
Yeah, it's still
Anyway,
right.
please
So
go ahead.
yeah, okay. So somehow, yeah. So here, that's one thing I didn't quite mention is, so in the end, we will show that in some cases this hope is true, but we have to up to a partition of the probability space. So this slight technical point I haven't explained. Okay. Okay. So now, so now I'm going to sort of introduce what I want to do today. So let's say we define a countable group to be a measure equivalent super rigid. If I have any other countable group, which is a measure equivalent to G, then that countable group is virtually G. That means they're isomorphic after passing to finite index subgroup or quotient by finite normal subgroup. And the, sort of the question which motivated this project is that we know that somehow amenable group are very flexible from the viewpoint of equivalence or measure equivalence. But if we try to construct some non-amenable group by gluing amenable groups in a complicated pattern, then whether we can sort of create some rigidity. So that's sort of why we specifically interested in the Higman group, because we're sort of interested in this sort of more general class of group which can obtain by gluing amenable group together in some complicated pattern. Okay, so now what do I mean by gluing? So so the group theoretical setting is think about a group acting on a cell complex such that all the cell stabilizers are amenable. Okay, so sorry. So this, for example, the most basic case would be if a group acting on a tree with amenable cell stabilizers. That would be, the group would be an amalgamation of amenable group. And then here, so if I have a group acting on a general cell complex with amenable stabilizer, so this will give rise to what's called a complex of group, would be a high dimensional analog of the base cell theory. Okay, so now the hope is that somehow if I have a group acting on some cell complex with amenable stabilizer, so even though the cell stabilizers are not rigid, but hope is that if X has some geometry and the intersection pattern of the cell stabilizer is quite complicated, then we could still get some rigid. So that's sort of what we want to do today. So this is what, so more precisely, so first I want to tell you is, first we have a sort of a general criterion guaranteed that somehow when we have this setting with this group acting on some cell complex with some constraint on the geometry of the cell complex. Then we also want some constraint on how the group acting on the cell complex. Then we can show that all the vertex stabilizers are M invariant. So in the sense which I introduced before. So in the sense that if you look at the corresponding Ob equivalence relation, then the sub-relation come from the action of those vertex stabilizers can be recognized. Okay, so this is the first thing I want to say, and the second thing I want to say is that so this in particular applies to generalized Higman group, and it's going to give rise to rigidity rigidity result for generalized Higman group. Okay. So questions so far? Okay, so now I'm going to define Higman group. So first I want to record the definition of Boltzmann-Sota group. So the Boltzmann-Sota group, an M is just that I take two generator A, B, and I consider this related A times B to the N, A inverse equal to B to the M. And then so I think there's several values of N and M, which we are probably very familiar. So and in particular, when A equal to M equal to 1, then the Boltzmann-Sota group is just a free abelian group. Okay. And then so now the definition of a Higman group is the following. So somehow it's going to be the Higman group is sort of we take a bunch of generators and I want to sort of glue this Boltzmann-Sota group together in a cyclic fashion. So it's quite interesting sort of we want to put this Boltzmann-Sota group together in an interlocking pattern. So you see A1 and A2 is going to generate a Boltzmann-Sota group, and A2 and A3 is generate a Boltzmann-Sota group, etc. Okay, so this is the definition of Higman group. And then so the reason for K bigger than 4 is that if K equal to 3, the group turns out to be trivial. So we have to start at least K equal to 4. Okay. And so I think Higman group is usually considered as some kind of counterexample to things or some kind of exhaustive examples. So for example, the first example of an finite presented group, which does not have any non-trivial finite quotient. And they're also as a counterexample to some conjecture of Grothendieck about finite convolution. And they're also considered as a potential example for non-sophic group, which is still widely open. So this is sort of an exhaustive object, but somehow this group also turns out to be quite rigid. Okay, so now we also define a slightly more general class of Higman group. So you see in the definition of Higman group, there's no need to stick to BS12. So we just consider this sort of stupid generalization, which is just I can just consider BS MINI in the definition of Higman group, not just the BS12. Okay. So now, well, this MINI are equal to the pair 1, 2, then we recover the classical Higman group. So this is the classical group we are studying. And the theorem we proved is that we have to assume K bigger than 5. Then, and we also assume all these MI and NI are non-equal. So it somehow, this will increase the chance of rigidity. I'm going to explain this assumption later. And then under these two assumptions, then all this generalized Higman group, they are measure equivalent super rigid. So that means any countable group measure equivalent to the Higman group is virtually the Higman group itself. Okay, so so here actually this K bigger than 5, we think may not be so necessary. The theorem could still be true when K equal to 4, but it's just we don't know how to do it. We think it must be true, but we don't know how to do it. I'm going to explain the difficulty if we pass from K bigger than 5 to K equal to 4. It's sort of more technical. And then this MI not equal to NI, I think that's actually quite important for rigidity. So if I set MI equal to NI, we may not have rigidity. Okay, so here is so I think the simplest counterexample we have is for mi equal to ni equal to 1. So in this case, the group is quite simple. So I just have a bunch of generators, and I have this cyclic commuting relation. Okay, so this is sometimes people call this a right-angled Artin group. Okay, so now I want to claim that this group is actually a measure equivalent to some much more complicated group. So now I'm going to construct a group G in a sort of similar way. So instead, I'm going to replace each of the generator by arbitrary group. So G is going to be, I take a free product of GIs. So GI is just some arbitrary group. And I have the same copy of I. So I is belong to this Z mod KZ. And now I'm going to impose a similar kind of relation. I'm impose that GI and GI plus 1 commutes. So that would be analogy of AI and AI plus 1 commutes. So this means that any element in GI commute with any element in GI plus 1. Okay, so this would be a more complicated group. And then what we know is that as long as each GI is infinite and amenable, then this group H is going to be Ob equivalent to this G. So hence H and G are measure equivalent. Oh, sorry. So somehow this shows that, so in particular, you can take GI to be arbitrary amenable group. So it is impossible to hope that the G is actually commensurable or virtually isomorphic to H. So this would be the lack of rigidity if we just set Mi and Ni equal to 1. So the problem here is that we somehow can replace this amenable, this Z2 subgroup by sort of more complicated amenable group, but sort of retain the group structure. But somehow what's interesting is that if you keep Mi equal to 1 and you change Ni equal to 2, so you would have a bunch of solvable Boltzmann-Sota group inside the Higman group. However, in that case, it's not possible to replace this Boltzmann-Sota group by more complicated amenable group and still stay in the same measure equivalence class. Okay, so this is sort of a very big contrast if we sort of change these numbers. Okay, so now I want to also mention some corollaries of the rigidity theorem. So let's first look at this slightly bigger group of the Higman group. So let's say, so this group turns out to be the automorphism group of this generalized Higman group. So let's say this F sigma is basically all the permutation of the generator such that it can extend to a group automorphism. Okay, and then it turns out that the automorphism group of the Higman group is rather small. So it's just the Higman group itself semi-direct product with this permutation of generator. And then so now what we have one as a corollary is that suppose we take this Higman group, generalized Higman group, which satisfy our previous assumption, then first we know that sort of almost all the basically the lattice envelope of this Higman group are more or less trivial. So this means that if I take some locally compact second countable group where the Higman group sits as a lattice, then the group is more or less the Higman group semi-direct with some compact group. Okay, so it does not have non-trivial lattice envelope. And the second is that so basically sort of as a corollary of the first one, so we know that somehow it also gives us some kind of statement for the rigidity of any Cayley graph. So basically we know that the Higman group has the standard generating set. We can also consider the Cayley graph of the Higman group with respect to any finite generating set. Then it turns out that the automorphism of the Cayley graph as a graph is always quite small. It's more or less this Higman group extended by some finite group. So this is sort of a rigidity result we can get from the ME rigidity. And also there's also an Ob equivalence rigidity result. So let's say we have the Higman group generalized Higman group acting on X. Same assumption before, so K bigger than 5 and MI not equal to NI. And we have some arbitrary group, arbitrary countable group acting on another probability space, free aggregate probability measure preserving. As long as we know these two actions are stably Ob equivalence, then they are virtually conjugate. The action are virtually conjugate. That means you pass to finite index, then the action are conjugate. And also we can replace the stably Ob equivalence by a weaker assumption. We just assume the cross product from Neumann algebra of these two actions are isomorphic. Then we can conclude that these two actions are virtually conjugate. Okay, so these are all the sort of the main theorem and the main corollary I want to talk about. So now I think in the rest of the talk, I want to mention how we prove this theorem. And also I want to mention that some of the tools in our proof could maybe potentially apply to more general class of proof. Okay, so now again, so recall that we have I'm going to follow the sort of the strategy I mentioned before. So I have this group. I want to take a collection of subgroups such that the measure equivalence or Ob equivalence can recognize the subgroup. So they are environments on one hand, and also I want to claim that this collection of subgroups, they have very rigid intersection pattern. So in this case, so we're going to define a BS subgroup of G to be a conjugate of a subgroup generated by two adjacent generators. Okay, so this is going to be a collection of subgroups, which we're going to claim that this collection of subgroup is going to be first the invariant and the Ob equivalence, and the second, they are rigid. They have some form of combinatorial rigidity. Okay, so this is what I just said. So first, I want to prove the BS subgroup are ME invariant in the sense I explained before. So basically, if you consider the action, then if you look at sub-equivalence relationship come from the action of this subgroup, then this sub-equivalence relation can be recognized. And the second, there's a combinatorial rigidity statement about the intersection pattern of this BS subgroup. So I think I'm going to explain the second point first because that's actually easier to explain. So okay, what do I mean by the intersection pattern is rigid? So now I want to define a graph which encode the intersection pattern of this BS subgroup. So this is actually defined by Martin when he was studying the automorphism group of Higman group. So it's a very simple-minded graph. So I just take a graph. First vertices are in one-to-one correspondence with BS subgroup. So one vertex for each of the conjugates, and then two vertices are adjacent. If these two subgroups have infinite intersection, then I just draw an edge between the two vertices. Okay, so this is the graph, and the rigidity, sort of the combinatorial rigidity statement we prove is that so again, so under the assumption, so here we only need K bigger than 4. And again, we need MI not equal to NI. Then, so notice that this group is going to acting on this graph because the group is going to acting on the collection of BS subgroups by conjugation. So it's going to acting as an automorphism of the graph. And basically what we showed is that any automorphism of the graph has to come from this way, has to come from the underlying group up to a finite index subgroup. Okay, so the automorphism of the graph is more or less the group itself. Okay, so I should say that just to draw analogy with other cases. So for example, in the case where G is a mapping class group, then the graph would be the curve graph. And then and there's also a theorem by Ivanov says that automorphism group of the curve graph is more or less come from the underlying mapping class group. Okay, so and in the proof of out of Fn, there's also some graph which play the role like this. Okay, so this is sort of the combinatorial rigidity part. So now in the rest of the talk, I'm going to explain the Ob equivalence part or the measure equivalence part. Okay. So here's a remark that the assumption here, for the combinatorial rigidity, we only need k bigger than 4. So we don't need k bigger than 5. Okay, so now to prove step 1, so we need some auxiliary things about the geometry of Higman group. Because our general setting is that we hope to have a group acting on a cell complex, such that the cell complex has some geometry. Then, so now I want to say the Higman group fit into this context. So the Higman group acting on some complex, and the complex is negatively curved in a perfect sense. So this is what I want to explain next. Okay, so what is the complex where the Higman group acts? Okay, so first, let's look at this picture. So first, let's try to draw a version of the presentation complex of Higman group. Okay, so this is not a standard presentation complex. So let me record that for any group that's a presentation complex, the one skeleton is a wedge of two circles, wedge of circles corresponding to a generator. And then I'm going to attach a two cell whenever there's a related. So now here, what I'm going to do is I'm going to slightly blow up the standard presentation complex. So let's say here, so for each of the relators, I'm going to consider a cylinder. So for example, for the relator A1, I'm going to consider a cylinder, which is basically A1 times an interval. And for relator A2, I'm going to consider a cylinder, which is A2 times an interval, etc. Okay, so this so this can be viewed as I just take the original presentation complex and slightly pull things apart. Okay, and then so now I also need to look at this relations. Okay, so now for the relation this, for example, A1, A2, A1 inverse equal to A2, A squared. So what do I do? So I see there's this A1 circle here, there's an A2 circle here. So now I'm going to attach your two cell. So this BS A1, A2. So here I'm going to see the presentation complex of the BS A1, A2. Okay, so such that the end of the cylinder are attached to this presentation complex. And here I'm going to do the same thing. So between A2, A3, so there's a copy of the presentation complex of the BS A2, A3. And I'm going to do this at every places of this vertices of this pentagon-shaped topological space. So now notice that if I do this, then I need to fill in. So now there's an empty pentagon in the middle. So I'm going to fill in the empty pentagon by a solid pentagon, by a disk. So this is the reason is because that if I don't have this disk in the middle, then I can take a loop which go around the pentagon once. That's not in the Higman group. Okay, so this would be the complex which I'm going to use to study generalized Higman group. So is the complex clear, or should I explain again? Okay.
Yeah, clear to me.
Okay, thank you. Okay, so now I want to say that for this complex, there's a natural map just mapped to a pentagon. So what you do is you just map each of these BS spaces just to the vertex of the pentagon. And I'm just map each of these cylinder. I just collapse the circle direction. So to map the cylinder to an edge of the pentagon. And this disk in the middle, I didn't do anything. Okay, so this would be sort of a projection map from the this pentagon, so pentagon-like space to the pentagon. Okay, and this pentagon, the fundamental group of this pentagon is exactly the Higman group, or the generalized Higman group. So now let's look at a more interesting complex if we pass to the universal cover. Okay, so let's say X tilde would be the universal cover of X. So let's think about what we see in X tilde. So in X tilde, we will see the lift of this BS subspaces. I'm going to call this the inverse image of this BS AI plus 1 in the universal cover. I call them vertex space. Okay, because they sort of correspond to the vertex of the pentagon. So so in the universal cover, I will have a lot of these vertex spaces. So what I'm going to do is in the universal cover, I'm going to collapse each vertex spaces to a point, similar to what we did downstairs. So downstairs, we just collapse each of the vertex to a point, vertex space to a point, and the cylinder to an edge. So upstairs, the lifts of this vertex space are still collapsed to a point, and the lift of this cylinder would be 0, 1 times r. And I'm going to smash the r direction, just to keep the 0, 1 direction. And then, so now I pass the universal cover and I collapse the vertex space and smash one direction of the 0, 1 times r. Then I'm going to end up with a space which I'm going to denote by k hat. So this space is the space we're going to be working with. So notice that k hat is just a union of pentagons, because for this pentagon, for this pentagon face in the middle, we didn't do any collapsing. The collapsing only happened on the vertex space and on the edge space. So this k hat would be a union of pentagons, and but it's going to, in generally, it's going to be many copies of pentagon glued together in some way, and this k hat is sort of encode the intersection pattern of how this vertex space and edge space intersect each other in the universal cover. Okay, so now, so this is k hat is a union of pentagon, and the second, there's a sort of natural collapsing map from the universal cover to the k hat, which is actually equivalent with respect to the group action. Okay, so now this k hat is what I'm going to use. So basically, we can put matrice k hat such that each pentagon has the right angle matrice as a right angle pentagon in the hyperbolic plane. Then it turns out that this space k hat is ket minus 1.
So it seems like this is where you use that the number of generators is at least 5.
Perfect. Yeah. So this is the place where I use the number of generators bigger than 5. So if the number of generators is 4, then I think here you can matrice each. So here, instead of pentagon, you have the square. You can matrice the square with the flat metric. Then here you get something which is ket 0. But it's going to be not hyperbolic. It's going to have plenty of flats inside. So, and then somehow we will see why somehow, at least for our current strategy of proof, the hyperbolicity is sort of important for us. Okay. So also, I just want to remind the definition of ket 1 quickly for those who haven't seen this concept. So it's basically a way of saying that the space has curvature less equal than -1. The definition is that I take a geodesic metric space ket minus 1 if the triangles in X are thinner than the triangles in hyperbolic plane. So what you do is I take a triangle PQR in X, and then I consider comparison triangle in the hyperbolic plane, such that the 3 sides P bar Q bar, the sides the distance between P bar Q bar equal to the distance between PQ, and same for the other 2 sides. Okay, so for any triangle in the metric space, I can build a comparison triangle in the hyperbolic plane, and want to claim that this triangle is thinner in the sense that if I take 2 points x, y on the triangle, I can take 2 comparison points x bar, y bar, such that P bar, x bar, the distance equal to the distance between Px, and etc. So by saying this triangle thinner, I demand that distance between x, y is less than the distance between x bar and y bar. Okay, so this is just way of saying that the space is negatively curved. So now the general theorem we proved is the following. So for group acting on, let's say, connected ket minus 1 piecewise hyperbolic polyhedral complex with finite shape. So this just means that we just use finite isometry type of cells to build the complex. So let's say, suppose I have a torsion-free countable group acting by cellular isometries on the space, then we're going to put a bunch of assumptions. So first, I assume that stabilizers with every vertex are amenable. This is true for the example we have in mind is Higman group acting on this k hat. The stabilizers are just this Boltzmann-Sota group, so they're amenable. And second, I want the edge stabilizer of infinite index in the incident vertex stabilizer. This is just a way of saying that I want the vertex stabilizer to be much larger than the edge stabilizers. That's why, so I can sort of, I can see the vertex stabilizer fairly easily. Okay, so and the second, the third condition sort of more substantial. So I want the action of G on X to be weakly asymmetrical. So this I'm going to define weakly asymmetrical in the next slide. Okay, so the last condition, I want the amenable vertex stabilizer to be non-isolated. So namely, if I take a vertex stabilizer, then I want to say this vertex stabilizer also intersects several other vertex stabilizers are known as infinite subgroup. Okay, so under this four condition, then we can conclude that the collection vertex group, they are actually invariant and Ob equivalence or stable Ob equivalence in the sense we described before. Okay, so this is the set of conditions. So basically, the more we should focus more on 3 and 4. Okay, which is sort of a more essential condition. Okay, so now I explain 4. So why I want the amenable vertex stabilizer to be non-isolated. So the counterexample comes from the relative hyperbolic situation. So let's say, this example is the basic reason for condition 4. So let's look at the group be a free product of two Z2s. And then, so we know that the group is going to act in the base cell tree with amenable stabilizer. It's going to be, the tree is going to count -1. But there's no way, I want to say that there's no way we can sort of categorize, distinguish the sub equivalence relation come from Z2. The reason is that it's possible to build an Ob equivalence between the action of Z2 star Z2 with the action of Z star Z, such that the sub-equivalence relation come from the Z2 action, coincident with the sub-equivalence relation come from the Z action. So now on Z star Z, I can sort of post-compose by automorphism of the free group. So this tells us that we cannot sort of distinguish the sub-equivalence relation come from the Z2 action. Okay, so that's so more precisely, if I take a sub-equivalent, if I have this Z2 star Z2 acting on a space, I can look at the sub-equivalence relation come from a Z2 action. I can also look at the sub-equivalence relation come from a Z action, which acting logarithmically on the tree. So there's no way I can distinguish these two sub-equivalence relation. Okay, so that's why somehow we want this condition 4, that the vertex group to be non-isolated. We want to avoid this relative hyperbolic situation where this vertex group does not quite intersect other vertex group. Okay, so this is the explanation for condition 4. And then, so now the key statement I want to say is that, so basically, so if I consider the free probability preserving aggregate action of this group on some probability measure space, let's consider the Ob equivalence relation R. Then basically we are able to recognize the sub-relations which arise from the action of the stabilizers. And then more precisely, we can basically this is the precise characterization of what is the amenable sub-relation. So I want to say that this sort of sub-relation come from the vertex stabilizers. They're sort of the maximum amenable sub-relation sitting inside a non-amenable world. But there's one caveat to this, because there are other maximum amenable sub-relation come from logarithmic actions. So to distinguish elliptic actions, the sub-relation from elliptic action and the logarithmic action, so the way is that I want this maximum amenable sub-relation to be non-isolated. So this will rule out amenable sub-relation come from logarithmic action. Okay, so now there's one more important ingredient is this weakly asymmetrical. Okay, so that's also another thing is going to play a role in the proof. So okay, so definitions, if I have a group acting on metric space, then the action is going to be weakly asymmetrical, means that as long as 2 points are far away enough, then the common stabilizer is small, is finite. Okay, so I think the way to think about this is that sort of the action, if let's say suppose here I'm fixing x, then the action sort of rotating around x. Okay, so that's sort of what if you look at sort of the action how the stabilizer of x acting on a large sphere of x, then any point in the sphere has to be moved. Okay, so this is sort of a rotating action. So once we have this rotating action, it's going to say that it's going to say something about the subrelation, amenable subrelation, which come from logarithmic action. So it's going to play a strong constraint. Okay, so now in the next slides, so I want to say a little bit more about the detail of how we prove it. So okay, so in the end, we want to prove this statement about to characterize the subrelations. Okay, so now I want to actually, instead of characterizing subrelation, so I want to introduce a proof which characterize maximum infinite amenable group. So this would be a baby version of characterizing sub-equivalence relation. So I want to say that if I have a maximal infinite amenable subgroup which is not isolated, in the sense that it's also intersect other maximal amenable group in an infinite subgroup, then the group going to fix a vertex of x. Okay, so now this is a purely group theoretical statement. But I still want to present a proof of this statement, which is the correct proof, which can be adjusted to characterize amenable sub-equivalence relation. Okay, so how would that work? So now basically, because here the subgroup is amenable, so it's going to have an invariant measure. So we want to somehow promote the invariant property measure to a fixed point. Okay, so now here I'm using that x is Gromov hyperbolic. So now I take x together with the boundary of x. So now suppose that the k is compact, then we can have a measure, invariant measure under the action of A. So somehow the problem here is that here k is going to be a locally infinite space. So this kx with the boundary is actually not a compact space. So here somehow we need to do a little bit more work to go around this compactness. So, but let me skip this point. So let's just pretend that k is compact. Okay. So now we have an invariant measure. So now we can look at whether the invariant measure is supported on x or supported on the boundary. If the invariant measure is supported on x, since x only has countable many simplices, I can just select those simplices with maximum measure, and that's going to give us fixed points. So now, if the measure is supported on the boundary, then what we do is that if the measure supported on the boundary has more than 3 points, I can use a barycentric map. So this is another place I'm using hyperbolicity to get a fixed point inside. Okay, this is reduced to case 1. And the last case is that if the support has only 2 points, then basically, so now let's think about what this means. So we know that this subgroup, basically the weakly asymmetrical assumption tells us that a subgroup cannot fix a point in the interior and fix a point in the boundary, because I assume that the action should be rotating. So that means if a subgroup fix a point on the boundary, then it cannot fix a point in the interior. So and it's particularly this from here we can actually not how to deduce that the amenable group has to be isolated, in the sense that it intersects all other maximum amenable group in a finite group. Okay, and then so this is roughly how the group theoretical argument goes. And then so what we do is to try to adjust this to the group theoretical argument. Okay, so I think I'm running out of time. So I stop here and thank you very much.
Let's thank Jingyin. Thanks very much for the talk. It's very interesting. So does anybody have a question? If you do have a question, just unmute your mic and ask.
Maybe just a quick question. So is it important that you put Baum's-Lag solitaire groups as a generalization of Higman, or you maybe can replace it with some, I don't know, amenable group?
Okay, so that's a very good question. So I think for this okay, so for this theorem, so it could be if we just want to say the vertex stabilizers are invariant, so we can use more general amenable group. And where we use the Higman group is that we prove this combinatorial rigidity theorem.
So on the page 15, I guess you tried to use the structure of Baum's-Lag solitaire, right?
Right. So this is the place. So when I try to prove that this graph is rigid, so that's the place I'm using some specific things about Baum's-Lag solitaire group.
Yeah, thank you.
Yeah, thanks. It's very interesting that the same strategy appears in the Furman's work on semi-simple Lie or simple Lie groups or higher rank lattices, and Kita's work on mapping class groups.
Oh, sorry. So this one, I should clarify that Furman's proof of ME rigidity somehow he has a different strategy.
Okay.
Maybe Furman can explain. So he's here. So but somehow the mapping class group and out of Fn follow the same strategy, and we're also sort of the same strategy for Higman. And I should say the quasi-isometry side is also a similar strategy. So I should say the quasi-isometry rigidity for higher rank semi-simple Lie group is actually also follow the same strategy, but for measure equivalence, it's not this strategy.
Yeah. Okay. I see. Yeah, it's very interesting. Right. Is there
yeah, so another question. Great talk and great work, by the way. Really interesting, but you set it up in a way that suggests that you do you have also quasi-isometric rigidity for Higman groups, or is it like
no? Right. So we're actually working on that. So in terms of we sort of believe that if we want to prove, if I have a quasi-isometry from Higman group itself, you should also map this Baum's-Lag solitaire group to a Baum's-Lag solitaire group up to bounded household distance. So, but at the moment, I don't know how to prove it. So that's just like a speculation. So.
I was slightly confused by one thing that you said quickly in response to Lewis's question, which is that the proof of QI rigidity for higher rank groups follows the same outline. I mean, are you just thinking of flats as playing the role that's played by Baum's-Lag solitaire groups here, or is there something else that you mean by that?
Oh yeah, I just mean the apartments, the flats, the top dimensional flats. Yeah. Sorry.
But no, that does make sense. I'm a little slow today. I do wonder if, I mean, somehow,
yeah,
in Alex's proof, you know, the group structure is hidden several layers down, and really, you know, it's the group structure of G and not gamma that's used, and it's used in the proof of the cocycle superrigidity theorem. But I think if you untangled all of that, it might actually look similar. I don't know. It's sort of hard to track because it, you know, the order of the proof is different, but the kind of group structure that's being used may not actually be so different in the end. I can't tell immediately.
Oh yeah, so this is something actually I wanted to understand. So this I should say this part, the Zimmer cocycle part, is the part I don't understand. So yeah, So that's a very good, helpful comment for me.
Yeah, but the main part for me was the step 0 that in this slide. That's the reducing. That's one piece which is common to all of those, but the step 1, step 2, they're different in mapping class groups and arting groups and other things that you worked on. But step 0 is the common piece.
Yeah, yeah. Also, it seems that step 0, the ME setting is sort of more complicated than the QI setting. So, yeah.
Is there a conjecture about like right-angled Artin groups or something? Like some of them should be rigid and others should be very flexible, I assume.
I guess so. Yeah, for rectangle. Okay, so maybe so actually for rectangle article they are sort of more flexible because somehow okay. So maybe the thing in this slide. So
yeah,
what we know is that any rectangle article group is actually Ob equivalent to graph product of amenable group. So basically, we can do this for any rectangle article group, but still stay in the same Ob equivalence class.
oh, okay.
But somehow so there's this notion of L1 measure equivalence. So somehow my sort of the conjectures with Horbez, so we sort of think that maybe there's a L1 ME rigidity for rectangle article group that could be possible, but may not in this setting. So.
Oh, okay. Sorry. Right. I mean,
So basically, the reason is that we're motivated by this work. There's a M1 ME superrigidity for the abelian groups. So somehow that going to rule out this way of just replace some amenable abelian group by some arbitrary amenable group. So that's why we think that might be true, but again, we don't know how to do it.
yeah, okay, this, yeah. Well, are there more questions or comments? Well, if not, let's thank Jingyin again. And
Thank you.
yeah, thanks. Very nice talk.
Thank you.
Okay, well, I guess that's it. So our next meeting will be on Friday. I don't remember if it's what time, but I'll email everyone about it.
Thank you.
Cheers.